Right, hi everybody. Colloquium time. So today's speaker is Lisa Upton. Lisa got her bachelor's degree in electrical engineering and physics in 2008, and then a master's in physics from the University of Memphis. And it was during her master's work she did an internship at NASA Marshall Space Flight Center, where she began working with David Hathaway. And during that work, she did some feature tracking to measure axisymmetric flows on the surface of the sun. But this collaboration resulted apparently in a science paper, which is really impressive. And also, Lisa relocated to Huntsville to continue her work with Dr. Hathaway. In 2012, she got a second master's in physics from the University of Alabama in Huntsville, and she was hired as a research associate. And then in 2013, she transferred to Vanderbilt University, where she continued working with Dr. Hathaway, and she got her PhD in 2014 from Vanderbilt University. Now, Lisa is currently working for the Space Systems Research Corporation, and she is a visiting scientist at HAO. And, well, I'll let her continue from here.
Thank you so much for that wonderful introduction, and I want to thank you all for coming to hear what I have to say about surface flux transport today. I'm just going to start with a brief little outline. I'm going to begin by introducing the solar activity cycle and the solar dynamo, and then introducing our surface flux transport model, which is called the Advective flux transport model, or AFT. I then go on to talk about how we're linking AFT with the photospheric magnetic field in AFT to other areas of the sun, up into the atmosphere and into the corona. And then talk about the latest predictions AFT has got for the next solar cycle. I'll then just have a brief recap, conclusions, and talk about some of my future projects. So I don't know if it's because they were the first structures observed on the sun or just because I've been looking at them for the last 10 years, but I usually like to start off my talks talking about sunspots. These are the first magnetic structures that were observed on the sun. They're cool, dark regions where the magnetic field penetrates through the surface of the photosphere. They are usually formed in groups that last anywhere from a few days to a few weeks. They were used to determine that the sun rotates in about 27 days, or one Carrington rotation. They have a characteristic tilt, referred to as Joy's law, such that the leading polarity spot is closer to the equator than the following polarity. And they follow Hale's polarity law, which states that sunspot groups have opposite polarity from one hemisphere to the other hemisphere, and that this polarity reverses from one cycle to the next. By observing the number of sunspots over time, Schwabe was able to determine that the appearance of sunspots is cyclic. And when new features of the sun were discovered, it was found that they also vary with this same cyclic behavior. For this reason, sunspots are now a commonly accepted measure of the solar activity cycle. We now have 24 cycles and counting. If we plot the sunspot number as a function of time, we see that the average sunspot cycle is about 11 years and has an amplitude of about 100 sunspots. The sunspots, if we plot the magnetic field as a function of latitude and time, if we plot the sunspots as a function of latitude and time, we see that the sunspots appear on either side of the equator, forming two bands. And that as the cycle progresses, these sunspots or active regions become more equatorward. The cycles also tend to overlap by about 2 to 3 years. Also, if we plot the magnetic field out as a function of latitude and time, then we also see that in addition to the magnetic field in active regions, the sun has polar magnetic fields that form a weak dipole, shown here and here. The polarity of this dipole reverses from one cycle to the next at about solar cycle maximum. In order to explain all of this interesting magnetic phenomena, back in 1961, Babcock created a phenomenological model to help explain the sunspot cycle. This model starts out at solar minimum with a dipolar magnetic field. Differential rotation wraps the submerged magnetic field and stretches the magnetic field, and as it's stretched, it becomes buoyant and rises up and forms these loops or active regions with the characteristic Joyce tilt and Hale's polarity. The turbulent convective motions of the turbulent convective motions then act to shred off the magnetic field from the active regions, where it's dispersed into the quiet sun, the magnetic network. The meridional flow and differential rotation then act to transport these flows, with the meridional flow preferentially transporting the following polarity flux to the poles, where it reverses the polar field and builds up a new polar field with the opposite polarity to start the next cycle. This is a nice movie that shows all of these processes in action. We see an active region here. The turbulent convective motions in the surrounding sun are shredding off the magnetic fields. They're then transported into the magnetic network, where they're carried by the surface flows to the poles. So several years ago, David Hathaway and I decided that we'd like to develop a new surface flux transport model. And at the time, most of the models that were out there were used in order to try to determine properties of the sun. And so they used contrived flows trying to figure out what exactly the meridional flow is doing. When we set out to create this model, the fundamental principle of it is that we wanted to make it as realistic as possible. So we wanted to take the observed surface flows and the observed magnetic field and see if we could put them in a model and come out with magnetic flux maps of the entire sun, butterfly diagrams that match the ones that we observe, polar field plots that match observation, and can we also reproduce active region evolution? So it's with this principle of let's try to make it as realistic as possible that we set out to create this model. We began by measuring the differential rotation and the meridional flow. We did this by using magnetic feature tracking. We averaged these flows over 27 days. We then smooth them, fit them to Legendre polynomials, and then we incorporate them into the model. By this time, David Hathaway had already done significant work looking at convection. He had been measuring the convection using Doppler images, and he had actually created a simulation that simulates the convective motion using an evolving spectrum of spherical harmonics. This simulation that he had developed was able to reproduce the observed velocity spectrum, the cell lifetimes, the cell motion, and the cell motions of the convective structures. And if we look at a simulated Doppler image, we can see that they're almost indistinguishable from the observations. And so this is the model that we use to simulate the turbulent motions in our surface flux transport model, which actually makes it rather unique because other models in the past have typically parameterized the turbulent motions using a diffusivity coefficient. One of the advantages of doing it this way is rather than just diffusing out the magnetic field as it's shredded off of the active region, it actually also acts to concentrate the magnetic field into the magnetic network. And so you actually get pictures that look like what you would see on the sun. In terms of the, yes, go ahead.
But You still have a diffusion coefficient in your code. What is that?
We do strictly for numerical stability. We have our original version was using a finite differencing scheme that was subject to CFL conditions, and so we would have artifacts that would appear, but this diffusivity is overwhelmed by the flows from the convective motion, so it really doesn't contribute substantially to the motion.
It's a uniform one.
At this time it is, but actually David has been working on creating one that it's actually a function of magnetic field strength, so where it only is applied where we need it. So, but that's in the works, something that's currently been working on. So, okay. In terms of the magnetic field, we can bring this into our model by two different methods, either by using data assimilation, and this is similar to what weather forecasters do. They assimilate the data as it comes in, and this allows their model to correct for any differences that occur between the data and the model. We've used this regime in order to create what we term as a baseline model. The baseline, because it is constantly being corrected with the observations, provides the closest contact with the observations, and it's a tool that we can use to compare with our other simulations to see how well are we doing. In addition to assimilating the data, we could also simulate active region emergence by inserting bipoles into the model. This is typically done by using active region observations and statistics. This regime allows us to investigate the details of the flux transport. If we want to change parameters and see how they might affect the system, we can do that using this model, using this regime. This regime is also what we use when we want to make predictions, because we don't know exactly what's going to happen in the future. This allows us a way to simulate what might happen. The output of our model are what we term as synchronic maps. These are instantaneous images of the magnetic flux over the entire surface of the sun. The outlined area you see here is where we are assimilating the observations from magnetograms HMI or MDI. And the field outside is where the model is actually transporting the flows and doing its work. And you can see one of the advantages I mentioned earlier was that because we explicitly apply convective velocities, we retain the magnetic network in the active regions, just like what you would see when you assimilate the data. So we now have baseline magnetic images, or excuse me, baseline synchronic maps for the entire HMI and MDI era. And these are currently available for each day at the 0, 8, and 16-hour time steps. We do, our time step is on currently at 15 minutes, but we only save the synchronic maps at 8-hour intervals just because of the sheer amount of data that we're going through. It might be quite tenuous to try to save all of that data. So if you put several of these synchronic maps together, you can create a lovely movie. This is a movie showing 1 year of the aft at work. You see active regions coming in where the observations are being assimilated. They continue to evolve, and when the observations come back around, any differences are corrected. But for the most part, they're in pretty good agreement.
Can I ask, on the back side of the sun,
sure,
far side of the sun, you said you use a frozen velocity field from the previous, or what exactly is velocity field on the far side of the sun?
On the velocity field?
Yeah.
So it's a combination. We use the convective velocity, the convective simulation to simulate the convective motions. It includes, I believe, all the way up to about an L of 250. Below that, the resolution, it just gets too small.
Not actually, I thought it was actually from the observations, the velocity field.
So in the sense that the velocity field has the convective motions that you observe on the sun, it has the same lifetimes and cell sizes in convection. As far as the differential rotation and the meridional flow, those are the observed meridional flow and differential rotation that we've measured.
Yeah.
So in that sense, they are the observed flows. The specifics of does this cellular structure match the cellular structure on the sun? We can't quite do that yet, but I know I'll talk about that a little bit more later on.
If I understand correctly, you're assimilating both the magnetic field but also the velocity field, actually, or not the velocity field at all.
The velocity field does change in time, so we're not assimilate. Well, when we're assimilating the data in the in that type of regime, the model is going to move the magnetic field wherever the observations say that magnetic field should go. So in that sense, you are getting
but not the velocity field.
Right, exactly. Okay. They're moving where the sun is putting them, but because we're assimilating the fields.
Yeah.
Yes.
Do you work with Mark DeRosa?
I've used his potential field source surface a little bit. I've only just moved it. Or no, that's Mark. Is that DeRosa? Yeah.
Because I saw something very similar at Shine last week, and I was wondering if you guys are aware of each other's work.
I know there are several other surface flux transport models out there. I know I believe Carl Henney's model also is using some convective flows, but I think theirs may be static. They don't actually involve in time like ours do, but I'm not sure.
I think it was Mark DeRosa's work
that
I saw. This one looks better, by the way.
So thank you.
This looks better.
All right, very good. All right, so next I want to talk about what we're doing with AFT in terms of space weather. How can we connect what we have, the photospheric fields that we have on the surface, with the atmosphere going up into the corona? And so this work began with a problem. One of the limitations of solar physics right now is that we don't actually have magnetic data on the far side of the sun. This is why a surface flux transport model that can produce these is so important. And so one of the problems that arises from this is the fact that when an active region emerges on the far side of the sun, we're not actually able to incorporate it into our model until it rotates onto the disk. And so there may be an active region on the far side that's there and evolving and interacting and doing things, but we're not aware about it until it comes around. So David and I sat down and we thought about it, and we're trying to figure out ways that we could improve this limitation. And we obviously thought about helioseismology and what we might be able to do. But then we thought about, while we got stereo over there now, let's use stereo and see if we can use 304, helium-304, as a proxy for active region emergence on the far side. So here I have an image showing our synchronic map, and another image showing the helium-304 synchronic map. And there's clearly some distinct active regions here and here that are not present in our maps. And so we wanted to explore what we could do. How could we use 304 to populate the far side of our flux transport model? So I went to the SDL meeting in Oregon, and while I was there, I ran across Ignacio Ugarura and Harry Warren, and they had been interested in far side active regions as well, and they had the same idea. In fact, Iñaki had been already busy at work characterizing the relationship between the 304 luminosity and the total unsigned flux in active regions, and that's what we have plotted here, the 304 intensity as a function of flux. And we see that there's this strong correlation, this nice relationship here. And so we began a collaboration to see if we could use this information to look at the long-term evolution of active regions, and can we use it to improve our far side imaging.
How about polarity? So you have...
Yeah, no, there's lots of good questions. So, before the launch of stereo, data on active regions was limited to the time window where the active region was on the near side of the sun. And furthermore, for magnetic data, it's further complicated by these limb effects that produce these artificially enhance the flux in an active region on the limb. And so getting a clear picture of how a very long-lived active region evolves over many solar rotations was quite challenging. This resulted in large time gaps for most of their histories. So we decided to take a look and see how can we do with 304 intensity and how can we do with aft, and what can these two different techniques tell us about one another. So here, what we've done is we've plotted the flux derived by the 304 relationship as a function of time. We've also, that's the green line here. We've also plotted the magnetic flux in two different bounding boxes for aft as a function of time. So the red is a square and the orange is the rectangle here. On this plot, you'll see that there's some gray bands. These represent the times when we actually had near-side observations, when we have HMI data to assimilate into the model. And so in these regions where the gray bands are, we've got very close contact with the observations. It matches what the observations say. And so what this tells us is that 304, the 304 proxy is in fact a good proxy for the magnetic flux. But then we also have these regions, these white regions, and that's where the aft model is working on the far side of the sun. And we see that the active region decay continues to follows the same pattern. And what this tells us is that aft can actually do a good job of evolving, decaying the active region when it's operating on the far side of the sun. And we also note that the two remain in very good agreement with one another for multiple rotations. So I guess that's one rotation and that's a second rotation. So there's 2 months that these two are operating in agreement. Yes?
So in the previous image, so white is when it's far side.
Mm-hmm.
How did you know that it was going to start decaying?
The model said that it was going to decay, and so
It just agrees with it.
And it just agrees. And the reason, the things that you'll see here, so there. Well, I guess let me go on because we'll discuss that a little bit more about the decay process. So this is not an isolated case. We've done this for several active regions. Now, admittedly, all of these active regions are very simple active regions. They're, the standard bipole. They're relatively isolated, so they're not interacting with a lot of crazy guys standing next to them. And we see that in most of these cases, we get in all of these cases, we get a close match for most of the time period.
In your model, how are you defining the unsigned flux in this active region? Have you defined an area?
That's right. So in this case, for the EUV, it's defined by that area, and then here we've got the square box in the red and the orange box in the rectangle. We wanted to use two different boxes because the active regions do get stretched out, and we weren't sure, how much these results might be affected by maybe the active region was stretched out and so part of it left the square box. And so that's why we did it in two different ways, just to kind of account for the fact that you've also got this differential rotation shearing that active region.
Do you actually destroy any unsigned flux in this by your model, or is it just diffusing away?
The decay is happening because it is canceling from interacting with opposite polarity flux. So it's happening in a very organic, natural way. There's not anything added on top of the model that says, okay, the active region needs to go away, so let's put some parameter in there to make that happen. It's very organic. It's just happening by the flux transport mechanisms on their own. And again, a critical aspect of that is the convection. If you just had a diffusion, you're not going to see this kind of profile. So let's see here. We do note that there are some cases that might be good examples showing where, for instance, here it looks like there's some additional flux that is emerging on the far side. And this is an example where the 304 intensity as a proxy can give us information that we don't have in the surface flux transport alone.
There are also some episodes where the flux from the 304 proxy seems to decay faster than the model would predict. Like in the bottom middle one, in the white band there.
Right here, yeah. And I'm going to get into that a little bit.
Right.
Let's see. Let's see if that was... Okay. So now that we have some kind of reassurance that this 304 proxy is telling us something reasonable, can we use it to tell us something about the long-term evolution of an active region? And so what we've done here is plotted the 304 light curves as a function of time. That's shown here. And it's a bit of a scattered mess, but we see there's some distinct features. You see a very quick rise followed by a much more extended decay period. The interesting thing that we found is that if we normalized these active regions, which we've done in the second, if we normalize these light curves, which we've done in the second plot here, and we've normalized them, I think, to 11158, normalized in amplitude and in time space, we find that this active region evolution is very consistent. They're the same behavior, and that this and that if an active region is twice as bright, it's essentially going to live twice as long. And so what this tells us is that if we know the peak intensity at 304, we can give you a very good estimation, as long as it's not interacting with anybody else, about how long that active region is going to live.
Peak intensity at what time?
I'm sorry?
Peak intensity at what time during its lifetime?
The peak the peak 304 intensity. So if you plot the active region, its lifetime, then where it has its peak intensity, and all of these have been lined up so they have the peak intensity here, based on that time.
If it's a new active region, how do you know if it's reached its peak or not?
Well,
so you can't predict only post.
Right. If you've got new flux that emerges into it, then you're going to have to recalibrate that estimation. But if you follow an active region and you say, okay, it's reached here and now it's going to start its decay phase, that at that point you can say, okay, we can estimate that it's going to live this long. There obviously are going to be cases, active longitudes, where an additional flux is going to emerge, and I think 11726 is one of those examples here. Here we see that when the reemergence occurs, that we actually get a higher peak intensity. But in the subsequent emergences, it actually still follows that same pattern. So. Here's some more examples. In these examples, the data assimilation process, where we're bringing in the flux from the magnetograms, is halted at the time of peak emergence. And so this is something we know after the fact. We know that the active region has its peak emergence at t equals 0. And at that point in time, we halt the assimilation process in the aft model. And we take a look and see, does aft still adequately decay the active region? And from these plots, we can confidently say, yeah, we're still getting a fairly good match for most of the time period. Now, there are cases like 1158 where you do have this excess, this rapid decay seen in the 304 intensity, but not in aft. And so we had thought that this was most likely due to some interaction with some other nearby flux. So we went back and we checked, and in fact on March 19th and March 26th, there were two very small active regions that emerged, interacted with the R active region, and then went away. And so that's what caused this excess decay in the 304 intensity in that particular case. Another thing that we noted, and this goes back to your question, Axel, is that there were some of the active regions where when the assimilation was cut off during the middle of the observations, we're right at the central meridian when we're cutting off the assimilation process. We see that there's this adjustment period that occurs where you have this very rapid decay during the first few days after cutting off that assimilation. And what's going on there is the model is adjusting from using the sun's convection flows, the convection pattern, to what the simulated convection pattern. And when you have two bipoles that are very close together and you suddenly put a completely different convective pattern, that polarity that's closest to each other is going to interact. And so what we found is that this effect was much more pronounced for smaller active regions that were closer together. It was more, a larger longitudinal separation. This effect wasn't as pronounced. And I think what was a good example here was 11259. Let's see, 11259. Which one is that? I think that's. Oh. I'm not sure which one that one is, but there was 11259 and 11765 had similar peak intensities, but 11765 had about twice the separation distance. And so it didn't really feel that effect at all when it was converting over to the simulated convective pattern.
Just a quick question, I mean it's related, but I really don't know.
Yeah.
What causes 304? What drives the 304 brightness? What physical process? Reconnection, so the more flux that's coming up and more flux that decays, kind of.
I would imagine that it's an emergence where the flux is interacting and there's some kind of heating mechanism going on. That's not really my specialty, so I really would, anything I could say.
There's a strong correlation with the amount of flux on the surface. That doesn't mean flux is still emerging during the decay phase, so it wouldn't necessarily light up.
That's right.
304, so there's definitely something.
But there's still, the flux is still probably, I'm not sure.
Yeah, but magnetic field does not necessarily eliminate 304 just because there's something happening behind it, right? Okay.
And that's a great question, and it's something that we will be looking into. So, I've told you that aft is wonderful and does this great job, but let me quantify it a little bit for you. And so what we've done here is we've plotted the amount of flux at different percentages of the peak intensity. So at 80% of the 304 peak intensity, how well do we match? At 60% in red, at 40% in green, and at 20%, do we still have a nice correlation between the 304 flux and the flux that we see in aft? And that's shown here. And then we can also plot a ratio of these two values as a function of time to see how well they agree with one another. And we see that for the most part, they're to within a factor of 2 of one another. And considering where we started before this, I think this shows a lot of promise, because before we had no idea what was going on at the far side. But here we can say, to within a factor of 2, we can tell you about what that active region looks like. And again, as we mentioned, it does, as I mentioned, it does look like there maybe it might be starting to spread out a little bit with time. But this isn't because of the model itself. This is because of interactions with other things that are maybe outside of the model. If another active region comes and adds flux, or cancels flux in an active region. So it makes that scatter a little bit larger with time. But again, for about 2 months, we're seeing the evolution to within a factor of 2. So now that we've got a little bit of information about how well the 304 proxy does on the far side, can we actually put it to use? And so the next step for us was to try to use 304 data solely to simulate the emergence of an active region on the far side. So I've described to you how we can use the 304 intensity relationship as a proxy to decide the amplitude of the flux. But what else can 304 tell us about the structure, the field distribution on the far side? Of course, it's not magnetic data, so we're not going to have polarity, but we do, we can assume that for the most part, our active regions are going to follow Hale's polarity. So we'll put that, we'll use that to determine our polarity. If we, Iñaki has also gone and plotted the separation distance for 19 active regions, and found this nice relationship here, correlating the separation distance we find in HMI versus a weighted standard deviation seen in the AIA images. And so there's this nice relationship here. If we then use that to create a circle based on the centroid of the AIA flux, that kind of gives us an approximation of what the separation distance between those two polarities are. So that's something. We then also checked to see, could we determine Joy's law tilt using 304 alone? And while in some cases we found some good matches, that was done with these green ellipses here, there were other active regions where it did not do quite so well. And so, for the purpose of moving forward, we'll need to do more work, and we use other intensities to maybe weed out this parameter. But for the purpose of moving forward, we're going to just use standard Joy's law tilt. So let's simulate far-side emergence, and that's what we've done here. We've taken a picture, a map of the magnetic field. We've halted data assimilation in advance so that all that's going in is the flux given to us by the 304 intensity. And we're manually placing in the active region. The total unsigned flux is assigned from the 304 intensities. It's split into 2 different pi poles. We use the separation relationship I just described. We use Joy's law tilt, and then we set them in motion. Again, no assimilation, data assimilation is going on at all in these. And we can see that we're getting very promising results. We're able to simulate the evolution of this active region based purely on these far side observations.
one other question, and I believe you do consider it, but all the active regions that are assimilated into your simulation, as they interact with one another, or do you treat them separately?
I think what we did in this case is we allowed the aft to decay without any assimilation for an extended period before putting this in, so that there wasn't any...
Right, no, I mean in general, like, when you run the code, you assimilate a bunch of active regions in it, and then they decay, but they start interacting with one another, right? So the flux does also further decay because of interaction of decay in active regions. In
the data assimilate, where we're operating under that regime. Here we're trying to isolate it, so that's not. But yes. So if an active region over here and an active region over here, and they get stretched out, and this falling polarity guy starts interacting with this leading polarity guy, yes, there's going to be some cancellation there. So how can we take this back up into the atmosphere? What can this tell us? What can this tell us about space weather? What can it do for us in this context? And this is very preliminary work that Iñaki has done. We submitted a proposal to Heliophysics GI to do this work. But so what he's done here is he's used the results from the aft model, the flux distribution from the aft model, where it's allowed to operate purely in the predictive case where we're using the far side to simulate this active region. And he's used that as the source in a hydrodynamic steady state model known as EBTEL, where heating is scaled as B over L. And so he's used, by using a potential field extrapolation to get the line of sight magnetic field, he's created these artificial images of what the active region may look like in EUV intensities. And that's compared here to the real observations. And we can see that we can do actually quite well. And again, these are preliminary. He's shown me some other work that I haven't got to look at in detail, but it looks even more promising than this. So I think we've got some really interesting work on the horizon. And this will hopefully allow us to answer your question. How does the active region evolution impact heating? How does that light up these EUV intensities? So maybe we can answer some questions like that. This is another just kind of little side project I did with Nishu Karna. Nishu Karna, she just recently got her PhD at GMU. I believe it's at GMU, but in DC. But she was looking at coronal cavities, and she was interested in the evolution of coronal cavities. So we did this just kind of like as a thought project to see how well can the flux transport model, can aft tell us where a coronal cavity might occur. And so what I've done here is I've supersaturated the field so that it's saturated at some extremely low value, like 20 Gauss or something really small, to really highlight where the polarity inversion line is. And so then I've plotted the location where she's measured the coronal cavity, and again this is going to be on the eastern limb where it's rotating onto the line of sight. And so we've plotted the location on the limb as a function of time. And we see that this cavity very beautifully follows this polarity inversion line as a function of time. So maybe you're doing some kind of coronal physics and you want to know where's the polarity inversion line on the far side of the sun. I can tell you. Again, we think that 304 is showing great promise for improving our knowledge of the far side. This is a potential field source surface image that was generated using aft as the surface magnetic field. We think by combining the aft with the 304 images, we can provide a more complete picture of what the global magnetic field of the surface of the sun looks like. And hopefully, it's our hope that by using aft in this global context, we can improve predictions like, do we want to know the solar irradiance? Do we want to know where the solar wind is? Do you want to know what other coronal models are going to tell you? And so we think we've got some very promising results that can be really insightful in these space weather type applications. Yes?
Where do you get the open fields from? Because they would be low intensity, so how do coronal holes fit into this picture?
Coronal holes?
Yes.
I think, so this is the potential field source surface model, where it's just extrapolating the polar fields fitting up to the 2.5 R sun, and so it's extrapolating where it thinks the coronal fields are. I would imagine that there might be places, for instance, right here, this might be indicative, where you have this large open field, might be indicative of where a coronal hole might be. So you could use this type of a potential field source surface on the aft images to see. I mean, I haven't analyze that in detail to see how well can we do that, but I think it would be really great to be able to do that, especially in some of these cases where we've put in some of these far side emerging active regions to say where a new active region might be, and maybe that impacts what the global picture looks like. So I think it would be really interesting to see, can we identify where a coronal hole is better than with this 304 knowledge. All right, so I know I'm running short on time, and I'm going to completely change gears on you, so I'm going to try to go through this pretty quickly. Next thing I want to talk to you about is more on the space climate type of scenario. What is the sun going to do in the long term? And one of the things that's become quite evident, I think most of us will agree, that the sun's polar magnetic fields at solar minimum are a great predictor for what the amplitude of the next cycle is going to be. There's 3 different parameters. The axial dipole is a measure of the polar fields. The polar field strengths above some latitude, usually taken to be 55 degrees. Also the geomagnetic index all show this very strong relationship between the polar field strength at minimum and the amplitude of the next cycle. We can plot the polar fields as a function of time, and we see that solar cycle 23, was about half as strong as the previous 2 cycles, and this was followed by another weaker cycle, cycle 24, and an extended solar cycle minimum, one of the weakest cycles we've had in at least 100 years. And so how can we use AFT to determine what the strength of the polar fields is going to be at cycle 24 minimum, and can we predict cycle 25 sooner using this information? To do this, we need a proxy for what magnetic field emergence might look like. In our case, we've used the previous solar cycles as proxies for simulating active region emergence. In the past, we've used cycle 17 to simulate cycle 23, and we used cycle 14 to simulate cycle 24. I'm sorry I'm going through this so fast, I just don't want to keep you guys too long. This is a simulation that we did with solar cycle 23 using solar cycle 17 active regions. The different colors represent different convective realizations. We want to know how much of an effect does the stochastic nature of the convection pattern play. In the model, we see that at cycle minimum, there's very little variation on long time scales, but that does become much more pronounced when you're looking at cycle maximum. Here we used cycle 17 to predict the reversal, post-dict the reversal, the cycle 23, 24 reversal. Here's the prediction that we made for cycle 24 about 3 years ago. I think it was 2013 we started this prediction. About 3 years ahead. Let's see here. And now that we have a little bit to compare to, this is what the observations actually showed. And we see that there's a lot of similarities between the two. Most distinctly, there was a relapse that occurred at about the time of 2014. Then we had a large rise period, which kind of leveled off. And all of these are captured all of these features are captured in this model, and the amplitude is in pretty good agreement nearly 3 years after the simulation was started. So this gives us a lot of confidence in what aft can do as far as predicting the evolution of the polar magnetic fields. We've now done a set of simulations to predict the amplitude of solar cycle 25. We are running the simulations from the start of 2016 through the start of 2020. Again, we're going to use cycle 14 active regions. We had good success with those in the cycle 24 prediction. Excuse me. We're going to use the So while we're doing this prediction, we want to also investigate some of these other stochastic effects that might come into play and might cause some havoc in our model. We're going to use 2 different sets of meridional flow. We're going to use 8 different sets of Joy's law tilt and 8 different convective patterns and see how much variation do we get. 32 simulations total. Again, we're going to use the meridional flow, the meridional flow that we're going to use one meridional flow that's going to stay constant as if it doesn't change from where it is at present. And then we're going to use another meridional flow that evolves to match what we would expect the meridional flow to do. For Joy's law, we're going to base this on the relationship outlined by Stenflo and Kosovachev in 2012. And then we're just going to use one realization of the convective pattern, but we're going to shift it by 45 degrees. So we're, in essence, using eight different convective patterns for each simulation. Here is the results showing the variability, the convective variability. So the red is the HMI observations. I believe the green is, yes, so the green is the meridional flow that was constant. The blue is the meridional flow that changed as expected. We clearly show a dipole strength in 2020 that's similar to what preceded cycle 24, but substantially weaker than what we saw for cycle 22 and cycle 23. While there is some variability due to the convective, the stochastic effects of the convection, most of the variability that we see here is due to the difference in the meridional flow profiles that was used in these predictions. As expected, the slower continued meridional flow produced a stronger axial dipole, and this is consistent with increased cancellation at lower latitudes, less flux moving up to the poles. Here's the variability that we saw when we looked at the different Joy's law patterns. We see that the axial dipole strength is again similar to what we saw for cycle 24, but we know that the variations due to Joy's law had a much more pronounced effect on the model. And after 4 years of simulation, this resulted in an uncertainty of about 15%. And it was clearly these variability due to Joy's law, randomization of Joy's law, was large enough to overpower the differences due to the meridional flow variations. We can also plot the field above a certain latitude. Again, 55 is nominal as a function of time, and this allows us to look at the hemispheric asymmetry. There has been a very strong asymmetry in the sun over the past several years, and that was of great interest to us. But we see that in all of our simulations, there's this reverse, let's see. The south weakens late this year and before recovering. And so the sun is in the process of correcting itself. The thing to note is that this is seen in all of the simulations, and the reason for that is that the magnetic data that's causing this is actually already in the model. It was in the map that we used to start off the model. Magnetic fields in the active regions that were there at the beginning of 2016. It's going to take about 2 to 3 years for them to get to the poles. And so since that magnetic field was already in there, that's why we're going to see it, and we see it in all of these models. It's all in our, because it was in our initial magnetic map, it takes 2 to 3 years to get there. We see it in all of those. And so this relapse in the south is something that we fully expect to see, and then before the polar fields will level off and be in quite a good agreement with the north. The asymmetry is on the order of about 0.16. Just as a comparison, cycle 22 was about 0.2, cycle 23 was about 0.16, and cycle 24 was about 0.11. Let's see here. To get to the prediction, the WSO gives the axial dipole strength of minus 1.6 Gauss at the start of the cycle 24, plus 3.21 at the start of cycle 23, and minus 4.4 at the start of 22. The average of all 32 of our realizations gave an axial dipole strength at the start of 2020, which is presumed to be the start of cycle 25, the cycle 24-25 minimum, was a value of 1.36, which is on the order of what we saw before cycle 24, although a little bit weaker. So we can confidently say that cycle 25 is going to be another small cycle, perhaps slightly smaller. We can also say that small cycles like this have deep extended minimum. So we expect that the cycle 24 minima will actually be quite long as well. So just real quick, let me just go through these conclusions real quick. AFT is a state-of-the-art model producing some of the most realistic magnetic maps of the entire sun. 304 intensity measurements can be coupled with the surface flux transport to establish the evolution of the total unsigned flux over long time scales. 304 shows really great promise for improving our knowledge of the far side picture of the sun. Combining AFT with these far side data allows us to provide a more complete picture of what the magnetic field configuration on the far side of the sun looks like. Again, cycle 25 is going to be small like cycle 24, and we expect that extended minimum. And just real quickly, some of the things that I have in the works. Of course, I'm going to continue working with Dave. We're going to continue to improve AFT. Again, one of the things we're looking at is, can we use a better diffusivity to mitigate some of the imaging artifacts we have. We're going to investigate surface flux transport processes, continue to make solar cycle predictions. I'm going to keep working with NRL, looking at, we want to look at more complicated active regions. Can we say something about their evolutions when you have complicated active regions interacting with nearby guys? What can we say about that? We want to look at the long-term flux dispersion and what changes might result in the EUV response. I've also been part of an ISI group led by Anthony Yates. I've given him a set of AFT results, a set of AFT synchronic maps, and there's a few people that are using those maps in some coronal models. I hope to get some interesting results out of that. And then here locally at HAO, I've been working with Mark Meesh, and our hope is to merge the AFT model or surface flux transport model with some of the dynamo models so that we can use the benefits of both. The dynamo models can tell us about the interior. We can connect, we can have a closer connection to the sun. And I think this is really some of the future of solar modeling is moving to this regime where we have models that can transcend regions. Can we get from the interior to the surface and up into the corona? And that's really where I'd love to go. And finally, we want to know what AFT can do for you. If you're doing some kind of coronal modeling or atmospheric modeling, can our flux transport help you? I'd love to know, love to collaborate. So with that, I know I've kept you a little late, so I don't know if we have time for questions or comments. Yes.
A question about technique. Can you say just at least a little bit more detail about how you dynamically assimilate in the flux transport model?
So these the simulations, most of the runs that you've seen here were done on a common filter type technique. It wasn't explicitly common filter, but it was weighted based on center to limb distance, which we take to be a measurement of the uncertainty in the data. So it's a common filter type technique. But we've actually been working on moving into a more explicit common filter, technique. And so that's kind of in the works. Eventually, I think it would be nice to actually see if we can get into doing something where we're using an ensemble Kalman filtering.
Okay. That's good.
Mary.
So you're using the 304 measurements from stereo, right?
Yes.
And they seem to be very valuable for your approach here. So that's an old workhorse now. So is there anything anything on the upcoming solar missions that's going to provide any kind of replacement for that when it dies?
I'm not sure if there's anything planned, but the important thing to note here is that this is kind of a validation of the technique. I don't know what instruments are in place or what intensities that they're going to have, but perhaps this can influence them. Maybe we can say, you know, you're not going to give us a magnetogram on the far side of the sun, at least give us some 304. Give us something that we can work with. I truly hope that that there will be some missions coming up that will give us some sort of far side data. I think there's a wealth of knowledge that can be obtained with far side imaging, even if we don't get a magnetogram. So I think that by doing this work, this is kind of showing, you know, how we can use this in novel ways, and maybe is something that we can point to say, hey, you know, give us another vision on the far side.
I don't know what the orbit of Solar Orbiter is, but it will
Yeah,
be magnetograms from a different angle,
right,
like,
yeah,
of the plane of the ecliptic.
right, yeah.
Following on, of course, the only, I guess, truly reliable far side technique, even though it's much, much lower resolution, would be the helioseismic.
Right, and I challenge you to tell me what anywhere close to what we're getting with these results. I mean,
I guess the strength of the active region signals that they see, has anybody tried to correlate them with the eventual strength of the eventual flux of the active region? Of course, it's two different times you're seeing it.
I think one thing that might be useful is to combine the two. I mean, helioseismology, it gives us probabilities. It says, oh, there might be an eruption over in this area sometime in the future. And if we can use that and say, okay, well, let's go and use our 304 intensity and look, do we have something there? I think there's great promise in doing that kind of analysis and seeing how maybe the two can complement one another. Yes.
There is this so-called ADAPT model.
Yes.
And they do, I think, use the far-side helioseismic imaging.
Right, that's correct.
As an extra input. Can you tell me whether they actually use turbulent diffusion as opposed to some kind of model velocity field for the diffusive properties, or what other differences are there between AFT and ADAPT?
I'd have to go back and check, but I believe theirs is one of the other models that uses a simulated convection, but they're, from what I understand, it may be static convection cells. They don't evolve in time. They don't have the same structure and lifetimes that we have in our model. And so I think that's where we have the advantage on them.
Any other questions? Right. Thank you so much again.
Thank you.